So I want to focus on this nice family of manifolds, namely real projective spaces, which are kind of a benchmark in homotopy theory. So I want to prove that the topological complexity of one of these things has an interpretation, has a couple of interpretations. One of them is as being the immersion dimension of these things, and this holds as long as M is different from 1, 3, and 7. And the other is that, in a way, a topological complexity of these manifolds measures the deviation of these spaces from being an edge space. In other words, TCPM is the smallest D such that there is a map PM cross PM, perhaps not into PM, but into a larger projective space, PD, which is sort of an H-space map, namely which is a deformation of the usual multiplication on the infinity version of this space restricted to PM cross PM. It's a homotopy deformation of that. So in a way, you may not have a map from PM cross PM into PM itself. Actually, these are the only cases where you do have such a map. But if you're willing to allow to increase the target space, then you could actually have this very natural a version of this multiplication in here. So let me, here's the definitions, relevant definitions. So suppose, so what is this? This is just the smallest, here, immersion of a manifold M is the smallest number D, so that this manifold admits an immersion into RD. And recall that an immersion, which I denote by this kind of symbol, is just a smooth map which is infinitesimally injective. All right, so such that there is an immersion. There are additional, let me say a few words about these special cases. Notes. In the three special cases, one actually has that the topological complexity then of PM for M1, 3, and 7 is, well, these are H spaces. And since they are H spaces, the topological complexity of this, I mentioned yesterday that this agrees with the category of these spaces, which is just M. And of course, these three cases correspond to these manifolds being parallelizable. And so they immerse in the smallest possible dimension, which is not M, because we are closed manifolds, but is M plus 1. So this number would be just one more than expected. But in the other cases, this number measures the immersion dimension and also this deviation from being an edge map. Now, alternative characterizations of the topological complexity are, well, there is another way of calling such a map. This kind of maps are called also axial maps. And this is so because the restriction, such a deformation, when it exists from PM cross PM into PD, is also called axial, in the sense that both restrictions to the axis are not null homotopic, are the other map, which is not null homotopic. Notice that there is only one map from a PM into a PDE as long as D is greater than M, because just by Brown representability, you have only either the inclusion, the equatorial inclusion, or the trivial map. So, and having such an axial map, there is a PM cross PM axial into PD if and only if some standard, the following happens. You can model this by maps if and only if there is a map from SM cross SM into SD, which is CIMAT 2 by equivariant. By this, I mean that if you keep fixed one of the coordinates, then the resulting map has to be equivariant with respect to the antipodal action, and the same thing for the other coordinate. So in other words, this has to satisfy that alpha of, if you are going to evaluate at a point and one of them is the negative of something, then you can just pass the negative sign to the other one, and also you can take it out. Okay, so the goal is to prove this result here. This is well, it's going to be a nice example of how you can use standard techniques in homotopy to prove this kind of result. But before going into the proof, let me also note that this result is sort of a singular property in a kind of a neighborhood of real projective spaces. Namely, you would, it is natural to ask, well, are there any other spaces with these, say, manifolds, for which the topological complexity of the manifold is just the immersion dimension of this, or does it have any differential topology interpretation, this thing? And it turns out it doesn't. For instance, the first thing to observe is that the topological complexity of a space, or a manifold if you want, is at most the dimension of the space if the space is simply connected. I'm going to be talking about that tomorrow. So at least if you're going to have some kind of an equality between these, this is of course usually larger than the dimension of the immersion dimension of the manifold if it is closed. So if you have a chance of having this kind of inequality, you better look for examples where you have a non-simply connected space. Now, what sort of natural generalizations of spaces which are not simply connected one has for real projective spaces? Well, there is a very naive one. You could take a length space, say of torsion a power of 2. Now, you could also ask, what is the meaning for topological complexity of these things, and how does it relate to the immersion dimension? And it turns out, I'm not going to prove it, but these are different. Namely, the topological complexity of L has to do with having maps of this form, which are S2L plus 1 cross S2M plus 1 into S2M plus 1, in such a way that with maps which are CIMAT 2 to the E by equivariant. Just as in here, if you fix one coordinate, then the resulting map is equivariant in that sense. However, the immersion dimension of L, and there is a way of making this precise. Now, I'm not trying to be precise here. The immersion dimension of L has to do with having maps as that which are only C2 by equivariance and satisfy the following condition, namely which satisfy that such a map alpha, well, if you have this property. for omega an element here. So what I'm requiring is that, okay, just as with signs here with signs you can just put the signs wherever you want. But now notice that you have an action of CMOT, the usual action of CMOT 2 to the E, this is acting on a sphere just in the way that this is defined. This is just the orbit space. So you have this action. And if you take such a scalar there, you can just put it in every place that you want. But you cannot take it out. You're not allowed to take it out. You can only take out the sign, namely omega to the 2e minus 1. So this is less restrictive. This is, of course, more restrictive. And as a consequence, one has that, in particular, the immersion dimension of such a space is less usually than the immersion dimension of, the topological complexity of the length space. And I have some charts of some concrete values, numerical values, but I'm not going to give it to you. Just say that in general.
So just to clarify, instead of CIMAT to the covariant using this other condition, and can you pull negative out of the Y slot too, or just the first?
Sure, because it has to satisfy the two things. So if this satisfies this is for any omega. In particular, minus 1 is inside this group, so you can just put it any place you want. Okay. Good. So, well, what other kind of spaces are there in a pi1 neighborhood of projective spaces which have a chance of resembling real projective spaces? There is another family of such, namely you can take flat manifolds, namely perpendicular lines, the space of perpendicular lines in some Euclidean space. If you take only one line, of course, you have projective spaces. And this is therefore a natural generalization of those things. And also notice that the fundamental group here is 2 elementary, depending on the number of k's here. However, in this case, the same property holds. You can find examples where this actually happens. You have these kind of inequalities. And even more striking is the following family of manifolds, namely the so-called projective product spaces. Well, these are a very naive generalization of those things. You take, instead of taking a sphere, like in a projective space, you take a sphere and you divide by the action of antipodal, by the involution of the negatives. Then you take just a product of spheres and you divide by the diagonal action, antipodal diagonal action. Then let me call this P n1 up to nr. And of course, you can assume that these things are ordered. Well, it turns out that the topological complexity of this thing, it depends basically on the first, the smallest ni's. So in general, you can prove that this is at most 4 times r n1. There are more specific bounds, although in general, this is not known what this value is. But here you have a general upper bound. It depends only on the smallest number here in this series, in this tuple, and the number and the total number of factors. But it's independent on the other ni's. And these other ni's could be just as large as you want. And of course, if they are really very large, the dimension of these will be also very large. And now the topological complexity is actually less than the immersion dimension. So even though these spaces have, notice that these spaces have just pi1 being CIMAT 2, and they are kind of a very naive generalization of projective spaces, they actually behave completely opposite to length spaces and flat manifolds. TC is much lower than even the dimension. So this is kind of a singular phenomenon for projective spaces. So let me now start talking about how you can prove such a result. Okay, so let me tell you first of all the equivalence between having an actual map and a map which is bi-equivariant. This is sort of a standard. Namely, the bi-equivariant maps cover, just as in the Borsuk-Ulam theorem, cover actual maps. Namely, notice that if you look at the homotopic classes of PM cross PM into P infinity, well, P infinity is the classifying space for CIMAT 2. So this is an Euler-MacLane space. So in other words, this is just, you are looking at the cohomology in dimension 1 with coefficients in CIMAT 2 of this thing. Well, that's easy. That's only CIMAT 2 plus CIMAT 2. And that means then, well, these are the classifying maps for double coverings of this thing. And so this says that up to isomorphism, there are only 4 double coverings of PM cross PM, and here they are. You can take the trivial one. That's 0 there. You could take the one that is detected on one of each of the axes. So you have this double cover. You have also PM cross SM via the obvious map. And the opposite one, you have also SM cross PM, and you have also the one that is detected in both axes. Namely, you can take SM cross SM, mapping into here. Now, this is not a double covering. This is a 4-sheeted covering. So you have to identify them. So take this Borel construction. Divide, like in there, divide just by the diagonal action. And of course, this, when you restrict it to one of the axes, you recover the canonical one. So these are indeed the 4. This corresponds to 0. This corresponds to 1, 0, 0, 1, or maybe the other way around, and 1, 1 in there. So what this means is that if you take suppose you have an actual map. Well, that only means that you can pull back this universal, this restriction of the universal double covering, the usual one, into something, but since it is actual, it has to be detected in both of the axes. So the double covering induced has to be this one. So the pullback here is nothing but SM cross SM. And since this is a pullback, this is CIMAT 2 equivariant. And then you can compose it with the obvious projection, and you would have a CIMAT 2 bi-equivariant map. So an actual map will give you a bi-equivariant map. And the other way is just the same. It's even more easier. Okay, now, so let me say how you can prove this. This is based, this result is due to Michael Farber with 2 collaborators, Sergei Juzbinsky, and I think it's also Sergei Tabachnikov. Now it's based, this is based on the following theorem, which I will also say a few words about of Adam, Gittler, and James. So this is Farber, Tabachnikov, and Juzbinsky, which says that indeed the immersion dimension of PM is just the minimal D so that there is an actual map of this sort, or a bi-equivariant map of this sort. This is the minimal D so that there is PM cross PM into PD actual. So the only thing that one really needs to do, what these guys did, was to say, okay, if you have an actual map, such an actual map or a bioequivariant map, then essentially what you're describing is a motion planning algorithm for planning on PM. So here's what you do. So I'm going to postpone to say something about this, and let me just tell you how you prove such a result. So let me start with an actual map. Suppose one is given an actual map. All right. Now, being actual means that the restriction to the diagonal is null homotopic, because it is non-trivial on each of the axes. So essentially, what this is saying is that the fundamental class here maps into x times 1 plus 1 times x. It is actual. And when you multiply them, it's just 0 here, because you get twice, but twice here is 0. So this actual map on the diagonal is null homotopic. So this is null homotopic. This commutes up to homotopy. Well, but fortunately, this is a cofibration, and therefore you can replace this by a homotopy by a map which is homotopic and which is actually constant on the diagonal, just because it is a cofibration. So you can assume alpha is constant on the diagonal. Alpha is constant on. All right, what can I do with such a thing? Well, I can cover it with a bioequivariant map. So I have here PM cross PM, alpha into PD. It's already constant on the diagonal. Now I have SM cross SM, and I already explained that you have this bioequivariant, CIMAT to bioequivariant. Let me call it beta. All right, and suppose that this map beta say, well, it lands inside our d plus 1, and so it has d plus 1 coordinates. So let me call them beta 0 up to beta d. Good. What can I do with this? Well, so what's my goal? My goal is to plan the motion on PM. So I want to look at PM, cross PM, cover the double evaluation map. It's 0, 1. And I want to define open sets here with local continuous sections in such a way that these open sets cover this guy. And these are continuous in here. That's the whole point. Well, I can define this as follows. Let me take UI to be, well, let me define first the first one. U0 will just be the projection of beta 0, that thing. Here pi is the canonical projection. Where is a pi here? This is pi. Well, I guess it's pi times pi. So I want to define, I'm taking here beta, so I'm looking at one of the components. So take the projection I into R, consider the complement of the 0, and take the inverse image here. And then this is pi. So that's what I'm doing here. Taking the inverse of everything, inverse image of everything that is non-zero, and just projecting that. Notice that that's an open set. And it also contains the diagonal, because my blanket assumption, this thing is constant. So notice that this is also constant. Namely, it has to send, it's constant on the diagonal, because this is so. The diagonal here will go to the couple of points that are just where this is constant, and this is connected, so it has to go to one single point, such point. All right, now I can also assume that that constant thing is, say, constant of diagonal with value, 1, 0, 0, 0, like that. So now it makes sense what I said. The first component sends the diagonal always non-zero. So this contains the diagonal. So that much is already covered there. And I'm going to do exactly the same thing for the other positive i's. This is going to be the projection of beta I inverse different from 0, except that I want to take the diagonal out. You'll see why. Anyway, the diagonal has already been covered by U0. Okay, well, I already have these open sets here. Now, I need to say, if I take a pair of points here in one of these guys, I need to give you an explicit, continuously give you an explicit map from one to the other. Now, what's the situation here? Suppose you have such a map, such a UI. Well, you can take, suppose you take x1, x2 in UI. Well, here's, sorry, these are lines. You take L1, L2 in U1, UI. So you have a pair of lines here. Well, they look like this. You have here L1, you have L2. And now what you could do is to choose a couple of points, say of norm 1 on these lines. There are 4 possible choices. You could choose this one and this one, or this one and the opposite, or the opposite and 4 possible choices. And now I would say, okay, if you fix one of these choices, and this is a choice, then I would like to move on PM, on the space of lines, I'd like to move this line towards this line in such a way that this vector maps into this vector. 2 of the choices have the same effect, namely this one, and minus x1 and minus x2 would do the same movement. But the other 2 choices would not do the same thing. But what I can do, notice that there is one choice in such a way that beta I of x1 and x2 is positive. It is non-zero because I'm requiring this to lie in this space. So this component is non-zero. So notice that then, for instance, beta I on minus x1, x2, because this is a bi-equivariant, it would be negative, and so on. So 2 of these choices give the same. If I insist that these representatives are such that this happens, then I would be choosing this one, or this one, and the movement is compatible here. The path is compatible. And notice that this is also continuous on this neighborhood, except when it is not defined. The only problem about this being defined is what happens. Okay, I didn't say it so, but the movement of one line into the other one is through the plane that they generate in this way. But what if they don't generate a plane? If they are the same line? If they are the same line, then you have L1 and also L2. And suppose that if one is not lucky enough and this is 0 and this is x1 and this is x2, and this is the one satisfying this condition, then you would like to move this line into this itself so that x1 goes to x2, but you don't know how to do it in a continuous way because there are too many through what plane. So in order to avoid this problem, you just look at this. Namely, on the diagonal, if the lines are the same, so if you're in the diagonal, then you already know that beta, in that case, beta 0 of x1 and the same one is 1, namely positive. So that's the pair of choices that you have to do. And now you have to move from x1 to x1. So there do nothing. And this is compatible. This is continuously compatible with the other kind of movements. So this is defining for you these, I just defined these maps, which are, yeah.
Sorry, if you trace the definition, if two lines are in UI, they're not orthogonal, right?
So can you say that again?
Is UI constructed?
Can you speak a little bit slower?
Yeah, is UI constructed so that if you pick two lines in UI, they're not orthogonal? That's the point. Okay.
Well, as long as if they are not linearly independent. They can be, if they are not orthogonal, at least that they are linearly independent. The problem is when they do not generate a plane. Okay. They are the same. If they are the same, and you have to really move to the other side, you would not know if you have to do it that way or what way. Okay. So, but that's not the point, because on the diagonal, this thing is always positive. And so you don't have this inconsistency. Well, that's kind of easy, the point set argument. The converse really uses homotopy, and so let me explain it. Esto. Okay, now for the converse. Conversely. Now, I'm going to suppose that you already have this motion planning algorithm, a bunch of open sets with local sections, and I have to construct for you a certain axial map. Well, first of all, notice that you have the following situation. So here is a map, E2, whose sectional category is topological complexity of this space. That's by definition. No? You want to find local section for this. Now, notice that I have SM cross SM, this double cover, this diagonal double covering of PM cross PM. Now, consider the following map, F. This map is going to send gamma, a path gamma, into the following thing. The class of this pair where gamma tilde is just a lifting of gamma through the canonical double cover. Namely, you have gamma is a map from 0, 1, it's a path, it's a free path on PM. And now you have your double covering. Let me call it again pi. And of course, we know that we can lift paths. And you have two choices now because it's a double covering. And so you have one lifting or the other, which only differs by sign. Now, notice that it doesn't really matter which one of these you choose, because if you chose this one, then you would have the sign here, but this is dividing by this indeterminacy. So this is well defined and it's clearly continuous. So you have this map. What can I do with this map? So, topological complexity of PM would be greater than or equal than the sectional category of this pi map, this P map. P. In other words, if you have local sections for here, well, you can just precompose with this map and you have a local section. That's kind of ridiculous, obvious. But you can have less number of local sections for this map. Okay, now what can I do with this map? The sectional category of this thing, notice this is the sectional category, P. What is this? Well, I claim that this is the sphere bundle associated to the exterior tensor product of the Hopf bundles. This is just the sphere bundle. And the reason is just as I was writing over here. You just have to analyze how many line bundles are there in PM cross PM. So the same as the double coverings. So it's And this is the corresponding one to that one, the one that is detected on both axes. So this is just the sphere bundle of that. And this is a line bundle. Now, what is the sectional category of the sphere bundle associated to a line bundle? Okay, well, what you're asking for is finding open sets with essentially a section for the sphere bundle. Or in other words, a section for this line bundle which is non-zero, and you can normalize it, which is never zero on this open neighborhood. So you want a section for this line bundle which is never zero, at least in this UI. And I would like to be able to extend this section to the whole thing. Now, you can, of course, do it if you, with a partition of unity, just with one piece. And you would have a section, but most likely this section would be zero outside. It might have some zeros. So what you could do then, okay, now you have several of these things. You have a UJ here, containing here, and another section. And now you can glue these together using a partition of the unit to get a global section. The problem is if you want to section this thing, which then would be a trivial bundle, line bundle, is that, okay, what some section, one extended section could be doing here, maybe canceling out with what the other thing does. So in order to avoid those cancellations, you just map into the sum. So that means that this is the smallest K, so that I can section as a global, continuous, nowhere zero section. A global, nowhere zero section by using this partition of unity. Okay, but now here comes the neat part. Namely, what does it mean? Well, it means that, okay, what I'm doing here, I'm taking PM cross PM. I already talked about this line bundle, this exterior tensor product line bundle. So let me just classify it. But I don't really want that line bundle. What I want is this multiple. So let me just continue classifying it. So the composite is that multiple. And I already know it has a section. So that means that I have a lifting into BOK. I have a lifting there up to homotopy. Now, of course, I could take the pullback of this thing. So I have this lifting. Now, what on earth could this pullback be? Well, this is a standard. What's the fiber? This is a pullback, so the two vertical maps share the same fiber. So you already know it. Jose already told us what's the fiber here. The fiber is OK plus 1 divided by OK, so this is SK. And so you have the same SK. And now what you want is essentially a double cover classified by this thing, which is universal for line bundles with a section when you multiply by that. Well, that model is just PK. Everything that I said applies to that, and that's actually the pullback of this diagram. So you have this map into PM, which is just a deformation of the usual multiplication. So that's an actual map. And there's your actual map given the so many sections here. All right, so that's the proof of that result. Good. Now, this is not really what, it's a variation of what Farber and the other guys did. But it's...
Sorry. So the key is that you can classify what that pullback is exactly, just using some...
Yes, that's it. Yeah, at the end, this is the key point. And this is a standard. This is classical. That's a pullback. All right. Now, what I want to say is that just as you have this, and then I have to say a few words about the Adam-Gittler-James theorem, the classical one. This is back from the 60s. Let me just say a few words about that. So that theorem, I just erased it, says that there is an immersion if and only if there is an action map. Action. So how can you prove this? What is behind here? Well, let me just recall a few constructions, again, classical constructions of the projectivization of line bundles, of bundles in general. So recall, suppose you have a line bundle. Any vector bundle. Any vector bundle. Alpha into X. Well, you could take the sphere bundle. This is just a bunch of spheres glued together, perhaps in a twisted way, according to the topology of the base space. And now I could projectivize each one of these spheres. So now I have the projectivized bundle. Right, like that. So this is a bundle of lines. This was a bundle of vectors of unit 1. This is a bundle of lines. There you have a bunch of lines over each point, but they are all glued together. All right. Now, notice that you could take still alpha and let me call this P, and take the pullback. Well, what is this? This is a vector and a line over the same point. But I want, and that just forms this bundle. But there is a tautological bundle. Namely, you can take a line, or a point here, and a vector, but that is in that line. So let me call that, there is a subbundle here, C alpha, which is a line bundle inside this this pullback thing. So this is nothing but a line and a vector in that line. All right, now this is a line bundle, and so this is a line bundle, and so how do I want to call it? Alpha. The projection is H alpha. So H alpha is classified, say, by a map from the projectivization. Let me just call it the same thing. Into P infinity. So for any bundle, vector bundle, you can define this map. And I want to call this is action. This is a generalization of action maps. And let me tell you why or how. Again, this is classical. This is essentially what Adam, Gittler, and James did. Okay, now what are the properties of these things? First of all, notice that if you have two vector bundles, one which is a sub-bundle of beta, okay, then you could take projectivizations. So these are just bundles of lines. Think of this as an equatorial inclusion on fibers. So you get the corresponding equatorial inclusion on fibers. Now, instead of having vector vector spaces on the fibers and an inclusion of vector spaces, you take only an inclusion of spheres. Think of it as equatorial. And then you projectivize, and you get what is happening on fibers. And now notice that this bundle, which I call C beta, restricts to C alpha. under this thing. Namely, this is just lines and a vector in that line. But I don't want all such lines. I want those that lie in this equatorial thing. And so the vectors should be in that line. So this just restricts into that one. And of course, if I classify this by a map, the composite would be classifying, this is a pullback, this is a restriction of this vibration, so this is the composite would be classifying the whole thing would be C alpha. So I want this, the first property, I want this naturality between the axial maps. The other is that, well, if you have, say, a vector bundle, and you think of the projectivization of this thing, so this is a bunch of projective spaces glued together. Now suppose you restrict it to a point. Sorry, this is not what I wanted to say. No, yeah, this is what I wanted to say. So the restriction of alpha is just a fiber. Suppose alpha is of dimension n, and the projectivization of this is nothing but Pn minus 1. So this is another pullback. Namely, here, essentially what you're doing is taking a bunch of projective spaces, each over one point of here, and then you're only taking the one inside over this point. So you only have this copy, one of the fibers. In other words, this is a fibration, and this is a strict version of what a fibration is as a pullback over a point. All right. Now, notice that if I classify, I have here C alpha. And I just said that this is also axial. In other words, that's basically homotopic to the inclusion. It's not null homotopic. So the point is that this is not null homotopic. This is the inclusion, essentially. All right, with this preparation then, I can do the following construction. Suppose you have an immersion. So suppose PM immerses in RD. All right, so the only thing that this means is that, okay, you can take a look at the tangent bundle, and here the tangent bundle, which is trivial, and you have this monomorphism of this map of vector bundles, which is injective on fibers. That's because this is essentially an immersion. It has to be a monomorphism on tangent spaces. Now, and actually, this is just the same thing as having an immersion by a result of Hirsch. So in other words, having a complement to the tangent bundle, having a normal bundle of certain dimension, then you have an immersion into the complementary dimension. So anyway, if you have this immersion, then you have this map. And so if you pull back this trivial bundle, that would just mean that the tangent bundle is a sub-bundle of the trivial bundle over PM. So I have this monomorphism of bundles. All right, so now let me do something very naive. Let me just add one. Let's just add one. So I have D plus 1, the trivial bundle. All right, so this is a map of bundles, which are sections and compatible sections. And now let me projectivize. Now I'm in this situation. These are bundles over PM. And let me just projectivize. So you have this map. Let me begin. So I have the projectivization of tangent plus 1 inside projectivization of D plus 1 epsilon PM. Now it's a matter of interpreting things. What is this? Well, this is a trivial thing. So what is inside here is just PM cross R D plus 1. This is the total space of this trivial bundle. And you want to projectivize the fibers. Fibers are trivially here. And you want to projectivize them. So this whole thing is nothing but PM cross PD. That's what you get if you projectivize. What do you get if you projectivize here? What you get is, okay, what is inside here? Well, it is a standard that if you add a trivial bundle to the tangent bundle, you get certain multiple, the right multiple of the Hopf bundle over PM, and you want to projectivize it. And there is an explicit model for this thing, namely, this is just a bundle over the sphere, over PM, but repeated. So what you're doing here is you want to projectivize something over the sphere with some kind of twisting of this dimension. So it's again a standard basic exercise to see that this is a model for the total space of this thing. Now, what if you projectivize this thing? What you get is, okay, these are essentially the fibers, although they are repeated. They are two of these fibers, namely over antipodal points, are being identified. When you projectivize, you essentially have to projectivize these things. You have to take unital vectors and identify antipodal points. And of course, you are here identifying diagonally. If you identify diagonally and then identify antipodal points in one of the factors, you're essentially doing identifying antipodal points independently on the two factors. So in other words, this is PM cross PM. And now I have this map up to here, which is axial by the things that I just said. And now notice that the corresponding map here, how is it classified? Well, it is classified actually, since this is trivial, it is classified by the second projection. So I have a map here which is axial in that sense, and notice, and here is something that you have to check, maybe that's an exercise. I have sections, compatible sections. I started with compatible sections, and those sections lead to sections of these bundles. Namely, if you have a point on the base and you know where to send it, then this is a non-zero vector, and just take the line through that vector. You have also a section for the projectivized bundles. So now you check that under these identifications, this section is nothing but the, sorry, that's what I want to say. Oh yeah, these things map into PM. Everything is mapping into PM, that's the base space. So I was working here, but everything maps into the base space, which is PM. And that section you have to check that is under these identifications, this section under these identifications is nothing, and this is very simple, than the diagonal map. And so you have here the corresponding section. And that section is just sending this thing into this because that was trivial. So what's the outcome? The outcome is that you have a map which is axial, namely it's non-trivial, homotopical trivial in fibers, and this is the fiber. So if you restrict it to this axis is non-trivial, at least on one of the axes is non-trivial. But on the diagonal, this map factors through here, and this is inclusion here, and then you project into the other one. It's completely trivial. So this is a semi-axial map, which is trivial on the diagonal, so it has to be axial on the other axis too. So let me just leave it as an exercise. So you get then this multiplied, the form version of the multiplication of PM. Good. All right, so that's the idea of the proof. Now, let me mention another such well, for me, surprising thing, namely that recall that on Monday I just introduced the symmetric version of TC. Namely, you want to plan the motion from one point to the other in such a way that if you want to plan the motion back, then you just use the same path, run backwards. So that defined for me, and I gave the explicit definition, which I will be recalling right now. So I define the symmetric TC of things. So I wonder what if this has some kind of a miracle also detecting this some kind of differential topology property of homotopical property of whatever. It does. And it turns out that this is not the immersion but the embedding dimension of PM. So namely the smallest Euclidean space where PM can be immersed but globally injected, in a globally injective way. Well, this admits an embedding. Except, perhaps, and this is because I cannot prove it in those cases. I'll just say a few words about that. In 6 cases, except perhaps for m is 6 or 7, 11 or 12, or 14 and 15. Maybe those are not exceptions if you insist this being a topological embedding, not a smooth embedding. Okay, by the way, remark, embedding dimension was extensively studied way ago, and in particular the smallest Euclidean projective space for which this number is not known is when P is 6. One does not know whether this is between 11 or 9. However, TC of P6 can be computed to be 9. So in a way, this is more accessible somehow, but gives a potential model for this number. All right, now how do you prove this? How do you prove this? Proof turns out to use less homotopy theory. It's more kind of a covariant thing, but not up to homotopy. It's just points at a covariant thing and just having beautiful thoughts. More generally, theorem, without exceptions, you can characterize the symmetric TC of PM as something that is called, I guess, the level of an involution in this case, or I guess it's also called the index of an involution. So this is just, let me just call level of, you take the configuration space of only 2 points on PM, 2 different points, 2 different lines. You have an involution by swapping the things. Let me call that involution tau. Do I want to call it tau? No, I guess I don't want to call it anything. CIMAT 2 is acting in there. And you have to add 1. So let me just recall what this level thing is. Definition. So suppose CIMAT 2, you have an involution on a space X. Suppose this is fixed point free, right? Now, well, then you can ask whether you have a way of mapping X into a sphere in a way that it is CIMAT 2 equivariant. And the smallest such M is the level of this involution. In other words, so the smallest equals the level of this involution for X. In other words, you can check that the level is nothing, but it's just obvious. You can take the double cover of this action. So this is a double covering. It's classified. So you can map it into B infinity. S infinity, you have this map, which would be C2 equivariant. There is no problem into mapping into this contractible space. But now you could ask, okay, maybe this is classified through a smaller version of this thing. So here you have PL, L for level, maybe I should say so, into SL. And I'm asking here to have an equivariant map. In other words, what I'm asking here is to have a pullback. And so this is the smallest projective space which classifies this double cover. So that's just the level of this involution. So how do you prove such a thing? Well, So here's what you can do. Well, let me do some remarks first. Okay, now, what is the level? Some examples and remarks. Suppose you have SL with the CIMAT2 antipodal involution. So what's the level of this thing? What's the smallest sphere which you can map SL by a CIMAT2 equivariant map? Well, Borsuk-Ulam theorem tells you that you can do it in SL, but you cannot do it any lower. So the level of this is that. Also notice that I have the version of this double covering, that double covering, that one over here, PL. And I could think of this projection map and think of the sectional category of this projection map. So what is the sectional category? Well, I claim that it's obvious that this is L. Namely, you have L plus 1 open sets with a section. The usual atlas of this would do it. And you cannot have less because you have, here you have a class in mod 2 coefficients, in cohomology with mod 2 coefficients, you have here a class, mapping 0 here, this is in dimension 1, mapping 0 here, and the product has height L. And whenever you have that, you have a lower bound for the sectional category, and that's L. So this is essentially L. So the level of this involution is the sectional category of that thing. And notice that this thing, by definition, is a universal cover classifying all coverings, double coverings, with level at most L, by definition. Well, that's then a general fact that the level of such a thing is nothing but the sectional category . So lemma, level of X with an involution is nothing but the sectional category of the double covering. This is sort of tautological, as long as you use, again, an argument using partitions of unity, again, as previously used. All right. So now, what can I do? I don't want that. So here's an example. I'm still postponing the proof of this result. Where is it? There. And notice that suppose that PM embeds in RD. And this will work even if this is not a smooth embedding, just a topological embedding. This is a subspace of RD. Then there is this Hefflinger map that goes from FPM to two distinct points, two distinct lines, into the sphere that sits inside RD that does the following. So if you have 2 points in PM, then think of them inside R of this Euclidean space and take the difference vector. So you can send this into Fx minus Fy divided by the norm. Since this F, this thing is, sorry, so many F, right? This is F, and this is the map G. So if you have two distinct points, they are still distinct here, and you just can take the difference between them. Notice that this map is C2 equivariant with respect to the antipodal action and the swapping thing. If you take the difference vector from one side to the other, and then in the opposite way, but it's just the negative. All right, so this is C2 equivariant, and therefore this situation would imply that the level of this involution, tau, is at most d minus 1. Or in other words, this plus 1 is at most d. And suppose that this was optimal, then you would get that the embedding dimension bounds from above this number. And that's just one of the inequalities over here, I guess. The opposite holds because in a certain range, the metastable range, having such an involution, having such a map which is equivariant by Heffinger's trick, I guess, is the same as having in certain range. Metastable range is the same as having an embedding. Okay, so that's pretty much what explains a little bit about this. And these, of course, are outside that range where you can just go back. The range holds from 16 on, but in previous numbers, you can just handle the situations by ad hoc methods. But so let me focus on how to prove this thing now. Not embeddings, just level and this thing. The proof is rather direct. So here's what you can do. So recall this diagram. This was the key diagram in the in the immersion dimension of that result. So I have the free path space PM. This is the double evaluation map. Its sectional category is TZ. Then I was considering this guy, this double cover. And I constructed this also called F map, which sends a path gamma into gamma tilde 0, gamma tilde 1, and the class. There. Now, well, but that's TZ, not symmetric TZ. For symmetric TZ, what I have to do is remove the diagonal. I don't want to plan the motion from one point to itself, so I have to remove the diagonal. So remove the diagonal, so you get FPM, 2 here, and there you get what I call the non-loops. These are just the free paths that do not have endpoints on the diagonal. I don't know how to call this, but let me just call it the non-loops on PM. What do I get here? Well, you have to remove all those points, the classes, which map into the diagonal. So you have to remove x times x and x times comma minus x, the diagonal and the anti-diagonal. So you have here m SM minus the diagonal and the anti-diagonal. And then you have to remember that you're dividing by this action. I'm going to denote it by D because it is diagonal action. This is CIMAT 2 diagonally acting here. Notice, since this is a fiber map, and I'm removing the same things in both cases, I have here the restriction of F. Now, I'm not still done for symmetric TC. For symmetric TC, I already removed the diagonal. I don't want to plan the motion between x to x. And also, if I know how to plan the motion from x to y, then the motion from y to x is. So I have to divide essentially by switching factors. So now, remember that CIMAT 2 is acting in the whole thing. At least it acts in here by swapping things. It acts here by reversing paths, and this is equivariant. And it acts here by also swapping factors. Notice that the whole thing is a CIMAT 2 equivariant, and so you can pass to the orbit spaces. So now you have non-loops, PM, orbit space, whatever that is. I call this whatever that is. And this is the bright space, 2 points, two sets of cardinality 2 in PM. And then here you have something similar. You have SM. Let me just keep a track on what this looks like. You have to divide by the diagonal action. And you have to divide by something that I called swapping. 2. This is, you have to divide by CIMAT 2 cross CIMAT 2. Two two different CIMAT2s acting in different ways. And notice that you have, that map is also equivariant, so it passes through there. Now, by definition, I guess I want to call this like that. The symmetric TC of PM is captured by this. You remove diagonal and you're making sure that this thing about reversing curves is taken into account. So this is just the sectional category of epsilon 2. And just having this map says that it is greater than or equal to the sectional category of the other thing. Now, I went, in the case of immersions, I went a long trip away, homotopic trip, just to try to find a map in this way so that both sectional categories are the same. I didn't do that, but then I used homotopy arguments. But in this case, just for free, there is a map the other way, which is very naive. What do you do? Here you have SM. And suppose you have 2 points which are not the same and not antipodal, here and here. And then you want to plan the motion, and you want to describe a non-loop here. Well, since they are different, you have just the geodesic, the shortest geodesic because they are not antipodal. Now, it is compatible, you just check that it is compatible with these two things. So that gives you for free this thing, and therefore, if you have a local section, then automatically you have a local section, and if you have a section, you have a local section, so the two things are the same of this thing. Later. Now, the good thing about this is that this is a double covering. This is a double covering. Essentially, you identify, you are taking here on other things, but you are also taking that into account. And so it looks like, locally, it looks like this thing, which is a double covering. All right, but so for a local covering, we know by the lemma, somewhere over there it was, that the sectional category of a double covering is the level of that thing. Namely, you have SM cross SM minus this divided by ds. And what's involution? The involution is that of associated to this double cover. What's that involution? Well, I claim that the involution is something that I'd like to call tau, say tau 1. Here, tau 1 acts in this space as follows. So you have tau 1 acting on here by sending A comma B at the level of representatives into whatever you want. You can send it into minus A comma B, but since you're dividing by the diagonal, this is the same thing as A comma B minus B. And since you're swapping, but the other two combinations are also possible. Those four things are the same there. So you have essentially acting on here, or in here, or wherever you want. It doesn't really matter. So it's the level of that thing. Well, then, the punchline, you want to get to this level, right? So, but what is that? Well, I have F PM, comma 2 on B PM, comma 2. This is the double covering associated to this action. This is the swapping action. So I have interchanging coordinates here. This is that action. Sorry, let me just put my ideas in order. You have here the swapping action. Well, I want to compare that with this, of course. This is not swapping. This is just changing one of the signs. But the swapping is inside in the space already. Well, you have to notice that what's a model for this? Well, a model for this is nothing but you have to have two lines. Well, they have representatives, so you have to have two vectors. But you have to, of course, avoid the diagonal anti-diagonal. And then you have to divide by, if you have two vectors, and the only thing that you care about was the lines, then you have to allow Z mod 2 act on each of the axes. You don't want to distinguish between this and that, and between this and that. So that's dividing by tau 1 and tau 2. 2 copies of Z mod 2. And then the action here is by swapping. I have Z mod 2, I have S acting on the whole thing. Here, by swapping. So the point is that there is an explicit map between the two constructions. Namely, depending on the time that I have, how much time do I have?
Say 2-3 minutes.
Right, so I'm just going to say what happens. What happens is that you have this SM cross SM minus diagonal anti-diagonal divided by diagonal swapping, and with an involution there by changing a sign down to B PM, comma 2. And here you have another thing. Here you have basically almost the same thing. But now identifications are tau 1, tau 2, and the involution that I care about is swapping. Here I have swapping, and here I have signs. And I want to compare the two levels. If I can show that these two levels are the same, that would be it. So it suffices to construct a map like here, so that it is C mod 2 equivariant. With respect to this involution here, and with respect to this other involution here. And it turns out that the same map does, you have only to change bases. Somehow you're changing bases, and just this allows you to interchange these three actions in another way. And the map is essentially, if you take an element here represented by A comma B, subject to these things, then this is going to, well, that's a couple, this is A, say this is B. They are not the same and they are not antipodal, so I have this crossing, I don't know what it's called. I can take the sum, and I can take the difference. What is this? I guess it's B minus A. Those are perpendicular, not only different, but those are perpendicular. This is just kind of perpendicularizing things. And then it turns out that at the level of representatives, this map, in this way, is compatible, sends these identifications into these identifications and respects this thing. So it's equivariant. And the same map going backwards does the same thing, the corresponding thing. So you already have a map that way and a map that way, which is Z2 equivariant. And so the level of that is just the minimal SL, so that you have an equivariant map. But then you can have this equivariant map, and that gives you the other equality for the level, and similarly the other way. Okay, so let me just stop.